All right, so we're going to begin today kind of continuing on with this review that we started on Friday. And in our Friday review, we talked mostly about just kind of what is an acid, what is a base. We got into a little bit of conjugate theory. And we talked about, a more quantitative way of looking at acid strength and predicting acid strength based upon structure. We're going to talk now a little bit about the pH scale. Now, in Chem 105, we really didn't cover the pH scale explicitly. We kind of just talked about it from a general sense. We looked at things like litmus paper. Is it red or is it blue? We looked at things like pH hydronium paper and went, okay, what is the color of the strip when we dip it into the water? Now, if you took Chem 103, or if you took chemistry in high school, you probably remember, you probably got some exposure to the pH scale there. And in that class, in that environment, what you would have known is that the pH is a measurement of the concentration of the hydrogen ion, which in this class, we will also interchangeably use the concentration of the hydronium ion, that conjugate acid of water that forms when water reacts with an acid substance. And that concentration is graphed, formed, used on a logarithmic scale. So when we think of the pH scale, we think of this scale between 0 and 14. And on the way far end of the scale, we have our acidic substances. And as you get closer to 0 and farther away from the 7, you tend to think of things as being more and more and more acidic. And on the other end of the scale, you've got your bases. And as you get further away from 7 and closer to the 14, you tend to think of things as being more and more and more basic. And then somewhere in the middle here, the exact range we kind of debate about. Generally, we think somewhere between 6 and 8, maybe give or take a couple of fractions either way. We think about things being neutral. Now, from a true definition of neutral, neutrality doesn't actually exist unless pH is at 7. But when we talk about neutrality for purposes like water purity, or looking at things like a swimming pool or a hot tub, or other recreational uses of water, chances are pretty good we're not going to get pH 7. It's going to be really difficult to do. So what it comes down to is what is an appropriate standard, what is an appropriate range where we don't have to worry about drinking water and having our esophagus burned by the acid or the base inside. And, same thing with swimming or bathing or anything else. Now, on the flip side, we can also look at pOH. pOH being the concentration of hydroxide ion on a logarithmic scale. And together, pH and pOH are going to equal 14. And the reason for that is because of the nature of hydrogen and hydroxide. Hydronium and hydroxide are basically the two conjugate products of water. And so when they are equal to each other, when we have neutral water, again, that's where we get our pH of 7. But you may have wondered to yourself, well, how did we ever come up with this idea of the logarithmic scale? Or why did we set pH 7 as our neutral value? It seems kind of weird. Why wouldn't we put neutral pH as pH 0 and go from a negative to a positive? Well, again, it comes back to the idea of concentration. And what we're really looking at here is a phenomenon in water known as autoionization. So basically how it kind of looks is water can get bored and ionize itself. So if there's nothing else for it to react with, it'll start to react with itself just so that it can go through the process of interacting and reacting. And when it does, what we'll see is that one water molecule will act as proton donor and the other as proton acceptor. And what we get when that happens is hydronium ion on one side and hydroxide on the other. And both of them are present at the same time. And at neutral pHs, both of these concentrations, the hydronium and the hydroxide, are equal to 1 times 10 to the negative 7th molar. So if I take the logarithm of that value, that's where my pH 7 comes from. That's why it's not pH 0 for neutral or any other kind of weird oddity. Now also notice, remember I told you before, the pH, or excuse me, the concentration of water is somewhere between 55 and 56 molar. And yet the autoionization yields 1 times 10 to the negative 7th molar. So what does that tell you about the equilibrium of this kind of reaction? It's very, 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 very reactant heavy. We're not seeing a whole lot of this, but we are seeing enough that we can notice it and we can measure it. Now, what this also tells us is that because water is capable of autoionizing, we will always have small amounts of hydrogen and hydroxide in our water at all times. If the two are neutral, or excuse me, if the two are equal, then we know that it is a neutral solution. Otherwise, we start looking at how does this equilibrium tip in one direction or the other. And so just one other note that we're going to want to make here. We already talked about this idea that hydrogen and hydronium and hydroxide are going to have this 1 times 10 to the negative 7th molar concentration. One value I want you to put into your head and store for later is this one. Kw stands for the equilibrium associated with water. And it's always found by taking the hydronium concentration multiplied by the hydroxide concentration. And if we are at normal conditions, 25 degrees Celsius, the value of that equilibrium constant is 1 times 10 to the negative 14th. Which means, since that value is constant at 25 Celsius, if I know the concentration of one of those species, because I'm dealing with a concentrated acid or a concentrated base, or even an equilibrium where I can solve an ice table and figure out one of those concentrations, I can use this KW formula to get the other. And this is going to be important for us because what we are going to see is that this relationship with water actually will start to spread out into some of our other understandings of acids and bases. So keep this one stored away. We're not going to use it quite yet, but we're going to use it in a number of different kinds of ways when we start using it. So again, just kind of a summarization here. pH is the negative log of hydronium. pOH is the negative log of hydroxide. If I multiply the two concentrations together, I get KW. If I break out the logarithms, this is how I get the pH plus pOH is equal to 14. This is how I get there. So this is more or less the algebraic breakdown that ends up with this equation. And again, this equation is going to be really useful to us because there will be instances where we will know the pH of something, but we need to actually know how to figure out the concentration of hydroxide. And so we're going to need to do a little bit of interconverting. And so actually one of the big goals for today is to get familiar with that interconversion process. So getting familiar and comfortable with turning hydroxide concentrations into hydronium concentrations, pHs into pOHs, kind of going all the way around this rectangle of familiarity here. Speaking of the rectangle of familiarity, here it is. So these four values, pH, pOH, hydronium, hydroxide, they're all interconnected with each other. And so if I wanted to do a calculation that turned hydronium concentration into pOH, you can see there's no direct line between the two. But I can turn the hydronium concentration into a pH by taking the negative log of it. And I can turn the pH into a pOH by subtracting that number from 14. Or I could turn the hydronium concentration into hydroxide using KW, and then take the negative log of that to turn it into pH, or excuse me, pOH. So what all of these show is simply that there are some interconnectedness between these values. And one of the things that we are going to need to do before we kind of break out our ice tables again is get familiar with this interconnectedness. So let's take a look at an example. Digested food leaving your stomach and entering the small intestine will undergo a pH change from 4.5 to 7.5. Convert these pH values to pOH, hydronium, and hydroxide concentrations. So what we are going to need to do is we have two pH values, 4.5 and 7.5, and we're going to have to push them around the other corners of this rectangle. Now, the good news is it's an incredibly repetitive process. So if I can figure out how to do it for 4.5, I can do the exact same thing for 7.5 and be perfectly okay. So what I'm going to do is this. You can actually do this in any order. But for me, turning pH into pOH is way easier than doing some of the other processes that we have to do. In fact, my general rule of thumb is I'm going to try to avoid using that KW expression just about as much as possible. Because when it comes down to it, what you'll end up having to do is KW is equal to hydronium times hydroxide. And so I've got 1 times 10 to the negative 14th is equal to some value times hydroxide concentration, which is going to be some sort of exponential. And so I'm going to have to take this exponential divided by this exponential. And if I slip up on my calculator and I put in a positive exponent instead of a negative, or flip the fraction accidentally, I'm going to end up with a whole host of problems. So my general rule of thumb here is I'm going to avoid using that KW expression unless I absolutely have to. If I have to, I'll go to it. Otherwise, I'm going to try to work around it as much as possible. And so the workarounds here to turn pH into pOH, I just need to subtract the pH from 14. Easy enough. 14 minus 4.5 is 9.5. Okay. So far, so good. To turn the pH and the pOH into hydronium and hydroxide, I'm going to have to use antilogs. Hydronium is equal to 10 to the negative pH power. Hydroxide is equal to 10 to the negative pOH power. So 10 to the negative 4.5 for hydronium. Is 3 times 10 to the negative 5th molar. One quick sig figs note here. Logarithmic scales can be kind of funny when it comes to sig figs. The general rule of thumb for logarithms is that the number of decimal places in the pH is the number of sig figs in the calculation, and vice versa. If I have a concentration with 2 sig figs, I'm going to make that 2 decimal places in my pH or my pOH. So since our pH here was only to 1 decimal place, our concentration is only going to have 1 sig fig. I said it's quirky, it's weird. We haven't done a whole lot with logarithms, but that is the general rule of thumb when it comes to significant figures, is look at the number of sig figs if I have a concentration, or the number of decimal places if I have a logarithmic function like pH. So by that same logic, 10 to the negative 9.5 is the concentration of hydroxide, which would be 3 times 10 to the negative 10th. So those were the concentrations of all of those species in your stomach. In your intestine, now they're going out to kind of close to normal blood buffering pH. We're going to do the same things. Turn pH into pOH by subtracting from 14. I would get 6.5. Turn the pH into hydronium concentration by taking the opposite antilog here, 10 to the negative 7.5. Is 3 times 10 to the negative 8th. And then 10 to the negative 6.5 for the hydroxide. Would be 3 times 10 to the negative 7th. Now, the way that you could check yourself for all of these, remember pH and pOH have to equal 14. So 4.5 plus 9.5 is 14. 7.5 plus 6.5, also 14. Also remember, hydronium and hydroxide concentrations should multiply together to give you Kw, 1 times 10 to the negative 14th. In each of these cases, you're going to get 9 times 10 to the negative 15th, which is, considering how much we rounded, pretty close. Remember what we talked about with equilibrium. If we are within a little bit of that 1 significant digit, we're actually okay. So we're talking about 0.9 versus 1. We're pretty good. And certainly with that level of estimation, you're going to expect larger rounding errors than otherwise. Which is also why when we measure pH in the lab, we will measure it to 2, if not 3 decimal places for that reason. The precision matters. All right, any questions on this kind of interconversion process? All right, so go ahead and try to tackle this one. Now, this one's slightly different. We're not interconverting in the rectangle here. I just want to know, what is the concentration of hydroxide ion, and what pH is that going to make the drain cleaner? So go ahead and work through that. and we'll come back in a couple minutes and see how you did. All right, let's take a look and see how we did. So the key to understanding this problem was we had to be able to recognize that this sodium hydroxide is a strong base. And so that strong base is going to turn into ions in water according to its stoichiometry. So we started with 1.2 molar sodium hydroxide. It would end up being 1.2 molar in sodium and 1.2 molar in hydroxide when it dissociated. So that means that our concentration of hydroxide is going to be 1.2 molar. Now, we can go back to our rectangle here, and starting with the hydroxide concentration, we need to get up here to pH. There are two paths that we could take. We could turn the hydroxide into hydronium, hydronium into pH, easy enough. Or we could turn the hydroxide into pOH, the pOH into pH. Now, just for completeness, I'll show us both of them. Based on what I just told you on the last one, the method I prefer would be turn the hydroxide into pOH, pOH into pH. But again, you could do either way technically. So what does that look like? So in approach number 1, I'll do that one in blue. Negative log of 1.2 is equal to the pOH. So the log of 1.2 is 0.079. So that would be negative 0.079 for the pOH. Now, this is going to raise a couple of eyebrows because we have a negative value for a pH or a pOH. That doesn't really register. The scale is supposed to be from 0 to 14. This is going to be outside of those bounds. And so that gets to the nature of when we have really concentrated solutions of really strong acids or bases, what we are going to end up seeing is that from a practicality standpoint, there's going to be a limitation to their complete dissociation. Eventually just going to run out of room in the solution for all of those hydroniums or all of those hydroxides. But from a theoretical standpoint, let's assume that they all do exactly what we say. The pH would be equal to 14 minus the pOH. So 14 minus negative 0.079 would give us a pH value of 14.079. Now, a couple of key factors here for sig fig purposes. Again, that 14 is an exact value. So we can think of it as 14.000 times a million zeros. Whatever value we measure, that's going to dictate the number of decimal places that we carry out here. So I guess if we're following our own kind of logic here, 2 sig figs should have led to 2 decimal places. So the pH we'd be looking for there is 14.08. Now, the secondary approach, wall it off here, we'll write it in pink. Starting with our hydroxide concentration still at 1.2 molar. We would use Kw is equal to hydronium times hydroxide we know Kw is 1 times 10 to the negative 14th. And again, this value here is exact. So think about an infinite number of point zeros after that 1. Times 1.2 molar. So 1 times 10 to the negative 14th divided by 1.2 gives us 8.3 times 10 to the negative 15th as our hydronium concentration. The pH would be equal to the opposite of the logarithm of that value. So the opposite of the log of the value there would give us two decimal places the same 14.08. So honestly, both approaches work. It's really a stylistic difference. Now, in problems like this one, it's not going to mean or make nearly as much difference because the value that you had for the hydroxide wasn't an exponential, wasn't in scientific notation. So you didn't have to really worry about making a mistake entering the scientific notation. But that is one thing that I know I struggle with sometimes is, hitting the exponent button on the right time and, getting the right scientific notation in. So I tend to favor pH and pOH methods more just because of that. Any questions with this example? So the next thing that we want to look at then is answering the question, well, what if we don't have a neutral solution? What if hydronium and hydroxide are out of balance? Well, with this understanding of autoionization, we can kind of put it into this thinking of it like hydronium and hydroxide being on a seesaw. If the concentration of hydronium is heavy, the hydroxide concentration is going to be light by contrast. We're going to have more hydronium, less hydroxide, and a pH to match it, being less than 7. If we go the other way, where I've got more hydroxide and less hydronium, it's going to tip the opposite way. Concentration of hydroxide is greater. That means we're going to have less hydronium. We're going to have a pH that is a higher value because it has a lower concentration. Now, when it comes to measuring pH, there are a number of ways that we can do it. One of the ways that we can do it is through instrumentation. We have pH meters. And the great thing about pH meters is that they are electronic devices. We can calibrate them. And when they are properly calibrated and we use them properly, they can give us really accurate results. The downside to all of that is, well, it's time consuming to do all of those steps. And sometimes we don't need to know the exact pH of a solution. We just need to know kind of roughly where we are. Think about the water quality tests that you did in Chem 105. You could have set up a pH probe and done the whole thing. Really, all you're looking for is the pH really acidic or really basic? If you got a value of 6, 7, 8 on those test strips, we said, good enough. Probably okay. Now, the other way that we can measure pH is the way that we have measured pH thus far throughout all of our classes, has been with indicators. Indicators would include things like litmus paper, test strips, pH paper, as well as chemical agents like phenolphthalein or other kinds of dyes, including the alizarin yellow R dye that we used in the Le Chatelier lab last week. pH indicators are really good at monitoring pH changes and giving us kind of a visual stimulus to help us, which is why we use them in titration so often, because we can look at it and go, okay, that's enough. Went from colorless to pink, and I can see the difference. I know I'm there. I know I'm close at least. But that can be kind of the downfall of indicators as well. For those times where we need an exacting value of the pH, we really can't get it that way. And so there are a lot of indicators that exist. And so some of these indicators, again, we are familiar with phenolphthalein. We have seen it in action. And we know that its color change from colorless in acidic solutions to pink in basic solutions helps us to give us a really nice visual cue as to when a acid-base titration has completed. I want to point out something to you because it's kind of interesting. Look where on the pH scale that phenolphthalein actually changes color. We won't actually see a color change in phenolphthalein until somewhere around pH 9 or 10. We'll start to see that kind of light pinkish hue somewhere around pH 8, 8.5, but it really won't show out until closer to pH 10. And yet, we're okay with that. We used phenolphthalein. We have used phenolphthalein for pretty much every single titration that we have done up until this point. Now, we're not able to answer this question now, but by the end of the week, we will. So I want you to think about this. And as we start talking more about acid-base chemistry, the answer might come to you. So I just want you to log this question in your mind. Why are we okay with that pH change where it is? Why don't we try to shoot for something like, say, a bromothymol blue that is going to change pHs at a much more neutral pH? Now, right now, you don't have the answer to that. But again, I promise you, by the end of this week, you will. And you'll come back to this thinking and say, oh, okay, that's why we do it. So just kind of ponder that one for the next few days. Now, we've already discussed a little bit about this idea of acid equilibrium. It's one of the things that we kind of ended with our discussion on Friday. This idea that acids are capable of dissociating, breaking into parts, and those parts are in equilibrium with each other. And since they are in equilibrium with each other, we can measure the directionality of that equilibrium using an equilibrium expression, using an equilibrium constant. And we call that equilibrium constant Ka. A in that case standing for acid, because we are looking at the specific equilibrium of an acid dissociation, as opposed to a gas phase reaction or some other equilibrium reaction. Now, all of our weak acid equilibria are going to follow this formula. The weak acid, HA, is going to react with water. The weak acid acting as an acid, the water as a base, giving us the hydronium ion and the conjugate base of that acid, which we will call A minus for lack of a better term. Now, depending upon what the nature of that acid is, that A minus can be a lot of things. You know, if it's acetic acid, we're talking about the acetate ion. If it's nitrous acid, we're talking about the nitrite ion. If it's sulfurous acid, we're talking about the hydrogen sulfite ion as the conjugate here on the other side. But because water is the solvent in this case and does not change in concentration, notice that it is not part of the equilibrium constant here, which means that our Ka value will almost always look like this. Hydronium ion multiplied by the conjugate base ion concentrations divided by the concentration of the weak acid, whatever it is. Now, there are lots of places where you can find values of Ka. Now, unfortunately for you and for all of us, there will be disagreements between the value of Ka for a given acid, depending upon the resource that you look. They'll all be around a general value, but you might see differences in sig figs. You might see differences in other places as well. For smart work is not going to ask you any question that doesn't involve an acid that you can find in the appendices of your book. So if you look at table A 5.1, which is in the appendices, it'll show up there. If you're in smart work and you've purchased the ebook, there will be a link that'll take you to the appendices when it is relevant and necessary. There are some questions here, as well as in the skill builders to come, that will use KAs, will use acids that are not found in that listing in your book. And so the lecture packet for this course contains those values.